welcome guys. So we were in discussion on Anova. We were discussing one-way Anova basically, and in our last class we have stopped here. Yeah, we have stopped at this point, right? So our SST, that is the overall sum of squares, the total sum of squares, we have seen it can be partitioned into two parts. These are the two parts. One is SS treatment and another is SSE, where SST treatment is the sum of squares, sum of treatment sum of squares basically. That means here we are trying to find out the difference of treatment average from the grand average. And SSE is the due to random errors, where we are trying to find out the difference of all the data from the grand mean. Oh, sorry, difference of all the data within a sample, difference of data from the treatment mean. Okay, so that is basically the variance within a treatment. So that is SSE, that is due to the random error. Okay, so now we will pick up each and every both the terms together. And first of all, so total how many observations are there? Total there are capital N observation. Why? Because there are total A level, and each level there are small n data. So total is A into N is capital N. So now what is the degrees of freedom for SST? Degrees of freedom will be, because there we are considering the overall, the total. So degree of freedom will be N minus 1. So now tell me what will be the degree of freedom for SS treatment. So by dividing by the degree of freedom, basically sum of squares divided by the degree of freedom will get a variance, right? So what is the treatment variance? To find out the treatment variance, the degree of freedom for SS treatment is basically A minus 1. A minus 1. So now what is the degree of freedom for SST? That is, of course, when we know this term and we know this term, definitely we can find out this term. That is definitely one way. Next, other way also we can also find out. See, there are total n replicates within a treatment, and each provides a n minus 1 degrees of treatment, right? In each treatment we have n degrees of freedom is n minus 1, and total there are n such a such populations. So total degree of freedom will be A into n minus 1, that is n minus capital N minus A is the degrees of freedom for SSE. So now first thing, so here there are two terms, SS treatment plus SSE. So we will take one term. So first let us take SSE. So this was my SSE terms, isn't it? Now here see in this term, you just see this term which I have marked with red. This term, if I divide by simple n minus 1, what do I get? This term yij minus yi dot bar. That means within a sample, within a level, I am trying to find out the difference between each data from the mean, isn't it? So I will get the variance of that treatment, variance of the ith treatment. Okay, so now this is again summation of I minus I is equals to 1 to A. So if I try to find out this, if I try to sum up of all the 8 level, basically what I will get, that is nothing but the same thing what we have got for pool variance estimate for the two population. Remember our two population pool variance estimate was, what was that? If you remember, n minus 1 S1 square plus n minus n1 minus 1 n2 minus 1 S2 square divided by n1 minus 1 plus n2 minus 1. This is the degrees of freedom for first one, this is the degrees of freedom for the second one. Remember, this was our pool variance estimate, and if you forgot how did you get this simple variance formula, S square is equals to this xi minus x bar whole square divided by n minus 1. So if this is sum of squares, this is nothing but sum of squares. So sum of square is nothing but s square into n minus 1, isn't it? So this is nothing, this is the pool variance estimate. So similarly, this term, if we divided this one term, if we divided by just 1 n minus 1, I get the variance of the ith level. Similarly, if this of all this, for all these levels, if I divide by the n minus 1 correspondingly, then basically it is nothing but a weighted sum of all the variances of all the levels. So that is nothing again the pool variance estimate, because here see we have considered initially only we have assumed that the population variances are same. So population variance are same, so we need to find out what is the population variance. So how did we do that? We found out the sample variance. From the sample variance, we come out with the pool variance estimate of the population. So basically, if we do this particular expression, from this particular expression, if we extend it. So, and then just I am dividing by this degrees of freedom of each level. So, this is what degrees of freedom of each level. If I get this is nothing but is equals to n minus a, and what is this term? This term is nothing but my this term. And what is this term? This term is SSE. So, SSE by n minus a. So, SSE by n minus a, what did I get this? This is nothing but my pool variance estimate. This is the pool estimate of the common variance within each of the treatment. See here, I am going slowly. SST is equals to, I got SS treatment plus SSE. Now, from SSE, I could see that SSE is nothing but if I just divide by the degrees of freedom, I will get the variance of all the pool variance estimate of all the population. So, that is what I have done. So, that means this term I have just added one extra term, that is divided by n minus a, and that becomes my pool estimate of the common variance within each of the treatment, and this term SSE by n minus a, I am using a different expression now. For that, let me use the expression MSE. Earlier it was SSE, now SSE divided by n minus a, let me use this term MSE. MSE is nothing but the pool estimate of the common variance. So, each population has a variance of this SSE by n minus a. Okay. This we got it from SSE. Now, we will come to SS treatment. Okay. So, this was my SS treatment formula. What is this? The sum of squares of the treatment average from the grand average. Now, if you recall the sampling distribution of the mean, which we have learned when we have learned sampling distribution, similar to central limit theorem only. Central limit theorem just talks about the normality. So, what is the sampling distribution of the mean? Sampling distribution of a mean specified that a sample mean computed from a random sample of size n from a population with mean mu and variance sigma square is a random variable which have an approximate normal distribution with mean mu and variance sigma square by n. What does this say? So, if we take a sample from a normal populations with mean mu and variance sigma square, so the mean of that sample, we have taken a sample, there is a population has mean mu and variance sigma square. From that population, we have taken a sample. So, now from the sample, we have found out what is the mean of the sample. Now, this mean of the sample, let me call it as x bar. Okay. Now, this x bar, it will have a sampling distribution, because x for different sample we will get different x bar, right. So, it will have a sampling distribution. Now, sampling distribution which is approximately normal. So, normal has two parameters, that is mean and the variance. What is the mean and the variance? So, mean of this sampling distribution is same as population mean, that is mu, and its variance is population variance divided by n. So, variance of the sampling distribution is population variance divided by n, that is sigma square by n. So, this we know from the sampling distribution of the mean. Now, we will be utilizing this. Now, see here. So, now try to think. And now what we have total A levels, A populations. Okay. From this A population, we have taken sample, total A samples we have taken, okay, each of size n. Now, this sample has mean mu I, each of this sample has mean of mu I, and each of this sample has this sample has variance, each of this sample will have variance sigma square by n. Why? See here. Suppose there are 5 population, we have taken 5 samples. This is 1 sample, 2 sample, 3 sample, 4 sample, 5 sample. We have taken 5 sample. Okay. So, from each one, suppose this is x1 bar, this is x2 bar, x3 bar, x4 bar, and this is x5 bar. And this x1 bar will have a sampling distribution which is normal. And what will be the mean of this distribution? Mean will be population mean. Suppose the mean of this population, that is the first population, that mean of this population is mu1. So, its mean will be mu1. And what will be the variance of this population? Variance of this population is a population variance divided by n. And what is the population variance? Population variance is sigma square. So, its variance will be sigma square by n. where its mean is mu1. Similarly, for this x bar, if we have a sampling distribution, what if we have a sampling distribution, what will be the mean of the sampling distribution? Population mean. Suppose this population mean is mu2, and what is the sampling distribution variance of this distribution? Sigma square by n. Here also it is sigma square by n. Why? Similarly, if you take x3 mean may be mu3, variance will be again sigma square by n. For x4 also mu4 sigma square by n, mu5 sigma square by n. Why sigma square by n for all the case? Because we have assumed all the populations, we have assumed that they have a the same variance, that is sigma square. All the population initially only we have assumed that they have the same variance, that is sigma square, isn't it? And we have also computed what is sigma square from the Anova entity. We have computed what is that. The pool variance estimated we have computed, isn't it? So pool variance estimated we have computed, that is, I think in the last slide only we have computed. Yeah, this is the pool variance estimate. This one, SSE by n minus a. What is this? This is nothing but the sigma square. This is nothing but sigma square. That is, so all the population has this variance. So since all the population has this variance, so some variance of all the sampling distribution also will be sigma square by n. Fine. Now, assuming that null hypothesis is true. Now, let us assume that the null hypothesis is true. If the null hypothesis is true, that means what happens? All the mu are equal. Mu1 is equals to mu2 is equal to mu3 is equals to, that means say it is mu. Okay. If we assume that all the null hypotheses are true, that means all the means, all the population, that means all the population have same mean, means as if all the population, that is as if we have taken a sample from a single population only. It's all the population are same. It is just an extended population. There is no difference between the population. If we assume that null hypothesis is true, all the samples as if we have taken it from a same extended populations. Okay. So assuming that all the population will be say mu1 is equals to mu2 is equals to 3 is equals to 4 is equals to 5, say it is mu. So if in that case, now suppose the different samples that we have taken, the means. Now suppose this is the, if considering that the null hypothesis is true, that means we, as if it is a single population. From all the population, suppose we have taken this 5 samples, and this suppose this is one is x1 bar, one value I got x1 bar, another value I got x3 bar, x4 bar and x5 bar. Okay, means as if from one populations we have taken some samples, 5 samples, from 5 samples I have got this data. Now if I want to find out what is the variance among these samples, variance among these samples is nothing but, this is the case, I want to find out the variance among these samples. So how will I find out the variance among these samples? Instead of x, here I have written y, so consider it is y. Same thing, y or x, whatever it is. So variance among this sample is yr bar minus, that is the grand mean, isn't it? How do I find out the variance? Variance is, I try to find out the each and every data from the mean, isn't it? So when I am taking this, so that means my mean is the grand mean. So divided by how many data? Total n levels. So it is a minus 1. So this is nothing but, this is equals to sigma square by n. This is nothing but, this is equals to sigma square by n, because all this population, we have seen all the samples, it has a variance of sigma square by n, isn't it? So we have taken only this samples. So if this is the case, that means the variance, if we now consider this this particular A samples, and if we try to find out the variance among these A samples, so this variance among these A samples, I got this, and this is nothing but sigma square by n, isn't it? Because I know the variance among this data is sigma square by n, variance among this data is sigma square n, variance among this data is sigma square by n, variance among this data is sigma square by n, variance among this data is sigma square n. If that is the case, then variance among this will also, I will get sigma square by n. Okay, so this value is nothing but equals to sigma square by n. Then by simplifying it a bit, so what did I get? Sigma square, you see. So my sigma square is nothing but this divided by a minus 1, and I have taken this side. So my sigma square is this by a minus 1, and how this value, you see, this portion, this is my this portion. Okay, So now what is the sigma square? That means SS treatment divided by A minus 1. So SS treatment A minus is the estimate of sigma square if the treatment means are equal. So if the treatment means are equal, I have considered null hypothesis. If all the treatments means are equal, then I have got this. If all the treatment means are equal, that means there is no change, there is no effect of the factor. If all the treatment means are equal, then my estimate of sigma square is this value, SS treatment by A minus 1. So see, I got two estimate of sigma square. One estimate of sigma square, I got it from the error, SSE. So that I found it for the random error, what may be the variance? That is all. From that also I got one estimate of sigma square, isn't it? That I got the pool variance estimate of all the population. That is the estimate of sigma square. That's one estimate of sigma square I got. Another estimate of sigma square I got, assuming that all the population means are same. Assuming that all the population means are same, I got another one estimate sigma square. Another one estimate of sigma square. So equation 1 provides us with two estimates of sigma square. One based on the inherent variability within the treatment, that is the MSE what we saw, SSE divided by this one, fine. So SSE divided by n minus A. So that is one variance estimate we got. Another variance estimate I got is SS treatment divided by A minus 1. So one based on the inherent variability within the treatment, that is MSE. Other based on the variability between treatment. Another estimate of sigma square, I got it by finding out the variability between treatment, considering that all the means are equal. Here I have considered all the means are equal. By considering all the means are equal, again I got an estimate of sigma square, that is MS treatment. In the earlier first estimate of treatment, here I was not bothered whether the means are equal, not equal, I was not bothered. I was just trying to find out the estimate of the variance by taking all data. In the second case, I tried to find out the estimate of the variance by considering that all the means are equal. So if there are no difference in the treatment mean, these two estimates should be very similar. So my second estimate of treatment sigma square, I have assumed that is also an estimate of sigma square. This is also an estimate. This is also a sigma square. This is also sigma square. This also gives sigma square. MS treatment also gives sigma square. MSE also gives sigma square. Sigma square. What is sigma square? Variance of the populations. Now this sigma square and this sigma square will be equal when because from this I got an estimate of sigma square. How did I get an estimate of sigma square? Assuming that all the population means are same. So if my all the population means are same, that means my both the variance estimates are same. If all the population means are not same, this MS treatment whatever value I will get, this will not be same as MSE. Okay. So if the two estimates are not similar, we suspect that the observed difference must be caused by the difference in the treatment means. Okay. So assuming that all the means are same, I got an estimate of sigma square. Now I have assuming that all the means are same and I found an estimate of sigma square. If all the means are not same, that the estimate of sigma square which I find, that will definitely not be equal to sigma square, that is the pool variance estimate. Okay. So if the two estimates are not similar, we suspect that the observed difference must be caused by the difference due to the treatment means. One difference is already there due to random error. So if the two estimates are not similar, that means the difference we are getting the difference because of the effect of the treatment, whatever treatment we had. For the music, because of the effect of the music, we are getting the difference in values. Because of the effect of the different treatment, we are getting in different values. Fine. So this is an intuitive argument. We can also show it using formal approach. How? So a test of hypothesis of no difference in treatment means it can be performed by comparing MS treatment and MSE. MS treatment gives us an estimate of sigma square, MSE gives an estimate of sigma square, two estimates of sigma square. How do you compare two variants? For comparing two variants, we have seen we use F distribution. Okay. So, if MS treatment by MSE has F distribution, what will be the degree of freedom? MS treatment degree of freedom is A minus 1, total number of levels minus 1. MSE degree of freedom is N minus A. We have seen why it is N minus A, isn't it? So, if the null hypothesis is true, then this MS treatment by MSE will have F distribution. F distribution means, remember the F distribution is something of this sort. So, F distribution means it will be in the acceptable range. MS treatment by MSE, it will be in the acceptable range. Okay. MSE is something I am trying to find out the variance of all the data. So, MSE will not change. Now, what happens if the means are not equal? So, this MS treatment, that this variance I will get a very bigger value. Okay. When my numerator value is bigger, so my F value, F is nothing by MS treatment by MSE. So, when my numerator value is bigger, I will get a very high F value. That means, my F value will lie in the critical region, in the rejection region. Okay. So, here if the null hypothesis is false, the expected value of MS treatment is greater than the sigma square. We will get a high value for us. So, A0 will be rejected if the calculated value of F0 exceeds the alpha significance level, that is the right tail of the distribution. Here we will be using only the right tail, because our F value will be, because it is our F is what? MS treatment divided by MSE. F value will never be smaller than MSE. It will never be, it is not possible to be smaller. Why? Because already whatever variance is there, it is there. How can we get lesser than that? So, only MS treatment will be more if the variance within the treatment, if it is more, so MS value will be a higher value. So, MS value is a higher value. That means, with my acceptance, my rejection region will only be in the lower tail, that means in this region. So, that is why it is always one way test, and that is we are trying to test is if F is greater than this value. Okay. This is always one tail test, and it is greater than a particular value. We will not check for lesser than a particular value. So, the expected value of MS treatment is greater than sigma square. So, okay. So, if F0 is greater than this, if the value of F0 what we calculate, if it is greater than F of alpha for this degree of freedom A minus 1 and N minus A, then we reject A0. Mind it, it is a one tail test with the significance level alpha. This formula, as I told you, it is pretty intuitive. The numerator term, that is the in the F calculations, the statistic defines the numerator terms, it defines the between group variability. Okay. So, this is the between group variability. This is this between group variability. Numerator terms, it decides the between group variability, and this term, this is denominator terms is within group variability, variability within the group. Okay. So, if this variability between group variability is bigger, that definitely between group variability is bigger, that means what? That means it does not belong to the same population, that means it belongs to different population, that means the population means are different. Okay. So, within group variance is larger and between group variance is smaller. So, F will be smaller, reflecting the likelihood of no significance difference between these three sample means. So, if between group variance is smaller, then what happens? I will get a very smaller F value. Smaller F value means it will lie in my acceptance region. So, it indicates that there is no difference between the population means of all the populations. Okay. As between group variability increase, sample means grow farther apart from each other. In other words, the samples are more probable to be belonging to totally different populations. If the between group variability is quite bigger, as if it belongs to a different populations. Okay. So, understood. That means from the what is the Anova entity? Anova entity gives us the two variance estimate. One is variance between the group, another is variance within the group. So, my f is, so when I have to compare these two variance, always I will be using f distribution. So, if my between group variability, which is in the numerator, if that variability is a bigger value, if the between group variability is a bigger value, then definitely I will get a very high value, and if the value f falls in the critical region or rejection region, that means what? That means my between group variability is very high, that is why I am getting such a high value, and then we cannot say that populations, all the populations are mean are same. That means because of the treatment there is effect on the populations. Because of the different treatment, the population means of the populations are different. So, it is convenient to summarize the results of analysis in a table for a one factor analysis. We can just give it in a table form. So, source of variance between sample, that is the SS treatment, its degrees of freedom is a minus 1. So, then from that we can find it is MS treatment. What is MS treatment? SS treatment by a minus 1 give us MS treatment. Then within sample it is SSE. Okay. Then SSE divided by n minus a, we get MSE. Then F is nothing but MST by MSE. So, basically now to conclude, so when we are trying to do ANOVA, exactly what we are trying to do? We are trying to do two things. We are trying to find out the variability between different groups. Okay. We are trying to find out the variability between different groups. That is one. Then second is we are trying to find out the variability within group. Okay. So, variability between group I am terming it as MS treatment, variability between group I am terming it as MSE. Now, if both the terms are equal, if both the terms are almost equal, not maybe same, but if there is no much of difference, if both the terms are similar, MS treatment and MST, if they are similar, then we can say that the treatment did not have any effect on the populations. So, whatever variance we are getting, the variance is maybe due to the random error. Okay. But if both the terms are very different, that means if MS treatment is quite high, that means the variability between group is very big. When the variability between group is very big, that means it definitely belongs from the different population. That means because of the treatment we are having some effect, and that is why the population means there is a change in the population mean. Fine. So, in this lecture we have seen that ANOVA identity provides us two estimates of sigma square, one based on the inherent variability and other based on the variability between the treatments. Okay. We have also seen the use of F distribution to compare these two variability, and thus gives a decision on the hypothesis. So, these are the references, and thank you guys.